There's an image that often comes to mind when talking about space. The digital clock of a control center, ticking impassively while outside, in the corridors, everything stands still. The screens are lit, the real-time graphs flow, yet the chairs remain empty. It's the unnatural quiet of an administration on pause, and it's precisely in this void that a new figure steps in, called to choose a course through a political and industrial storm. The issue isn't merely reopening the doors. It's deciding whether the next phase of American exploration should be orchestrated as a grand traditional public enterprise or as a modular ecosystem, with the private sector providing the operational muscle while strategic vision remains firmly in the agency's hands. Whoever takes the helm inherits a paradox. On one hand, a scientific machine that has landed robots on Mars, telescopes at Lagrange points, and astronauts in low Earth orbit for over 20 years. On the other, a context where commercial launches have become routine, costs per kilogram have dropped by an order of magnitude in a decade, and private constellations already sketch the map of orbital infrastructure. The question, then, isn't whether to change, but how fast, and with what priorities. The most radical hypothesis is to refocus the agency on great frontier missions: human return to the moon with sustainable architectures, preparation of trajectories and technologies for Mars, space observatories capable of resolving open questions on dark matter and biosignatures, while outsourcing many baseline services. Deployment of small payloads, platforms for microgravity experiments, cislunar logistics, even parts of the communications infrastructure. This doesn't mean dismantling internal expertise. On the contrary, it means concentrating human capital on areas where public advantage is irreplaceable: safety certification, open standards, high-risk technological research, continuity of climate observation series, and the protection of that common good we call access to space. A NASA that acts more as architect than bricklayer can accelerate the pace of innovation, provided its direction remains clear and contracts are designed to reward measurable outcomes, not promises. Within this framework opens a chapter that seemed like science fiction only a few years ago but has now, thanks to the energy hunger of artificial intelligence, become startlingly real: data centers in orbit. The idea fascinates for simple yet powerful reasons. Above the atmosphere lies a stable energy source of 1,361 watts per square meter before losses. There are no clouds. No day-night cycles if you choose suitable orbits or use well-sized storage. There's no local impact on soil, water, or power grid. And waste heat, on Earth requiring kilometers of cooling towers or costly refrigeration solutions, can in space be radiated away through panels optimized for the desired operating temperature. The flip side, however, is harsh. Latency, reliability, radiation, maintenance, orbital collisions, cyber resilience, hardware upgrade logistics. Hence the debate. Some dream of heliosynchronous, computational parks. Others propose dockable modules, robotic maintenance, and optical inter-satellite networks composing a distributed supercomputer. From an engineering standpoint, the bottleneck is evident: bandwidth between nodes. Given the same algorithm, bringing data to compute costs less than bringing computation to data, and in space, datasets aren't tethered by undersea cables but by radio and laser links. Today's optical inter-satellite links demonstrate hundreds of gigabits per second across thousands of kilometers, but an efficient distributed data center would need to multiply those capacities with safety margins, maintaining sub-millisecond latencies between nearby nodes and using retransmission protocols aware of errors caused by pointing or thermal jitter. That's why some concepts envision constellations of micro-modules spaced a few hundred meters apart in sun-synchronous orbit, where repetitive geometry simplifies thermal and power planning, close enough to behave like a cluster, far enough to reduce risks during evasive maneuvers. Energy and heat inevitably become a game of surfaces. Let's fix ideas. If one orbital rack consumes 15 to 30 kilowatts, powering 1,000 requires tens of megawatts continuously. With onboard photovoltaic efficiencies around 30% and annual radiation degradation, We're talking colossal panel areas, deployed and stabilized without disturbing the fine attitude control of optical links. But the real constraint is heat disposal. At 300 Kelvin, radiated power per square meter is a few hundred watts. For thermal megawatts, radiator fields larger than the panels themselves are needed, with low-pressure fluids, high emissivity materials, and joints tolerant of prolonged exposure to thermal cycles and micrometeoroids. It's an energy balance that demands creativity. Raising operating temperatures to increase emissivity, using jet pumps, segmenting into petals to isolate faulty modules, combining heat pipes and two-phase loops. Then there are the particles. Every chip in orbit converses with an unforgiving environment. Single event upset, latch up, total ionizing dose. Memories must have aggressive ECC, registers replicated, silicon layers engineered to endure proton and electron fluxes seen on Earth only in labs. Shielding is possible, of course, but every millimeter of aluminum is masked to launch and decelerate. Here come resilient hardware-software architectures. N-modular redundancy with voting, self-healing ephemeral containers that recompile corrupted modules, continuous snapshots across physically separated nodes, and protocols embracing controlled degradation rather than chasing the illusion of perfect reliability. In other words, a supercomputer that accepts and embraces the fact that it lives in space. All this, however, only makes sense if the economic pivot holds. The empirical rule is simple. Cost per kilogram decides nearly everything. If putting a computational unit into orbit costs as much as building 10 on Earth, space wins only in special cases. Processing that must remain near orbiting data sources, Earth observation, space situational awareness, interplanetary relays, extremely bursty loads exploiting the sun as a battery, and night as a thermal rest window, or scenarios where the ground footprint is unsustainable. The advent of reusable heavy launchers and next-generation architectures drastically lowers the threshold, but the final mile remains. Not just moving satellites, but their life cycles, upgrading GPUs, replacing faulty modules, recycling materials in orbit to avoid graveyards of discarded hardware. Without mature robotic maintenance, hidden costs explode. In this transition, the federal agency can play an extraordinary role if it embraces the stance of impartial arbiter, defining standards for interoperable optical links, publishing radiation hard testing suites measuring the resilience of entire AI pipelines, not just transistors, funding demonstrators with strict cybersecurity requirements, and above all tying every public dollar to verifiable milestones on energy efficiency and debris mitigation. It's easy to be captivated by the notion of servers in eternal light, but a computational constellation without rules risks becoming a multiplier of collisions and fragmentation. Orbital corridors, active separation geometries, and robust deorbit plans are essential, in essence, a zoning law for low Earth orbit. If the new administrator chooses this path, they will also have to resolve a cultural tension. How to preserve the educational and scientific mission of the great agency in an era ruled by market timelines and metrics. The most convincing answer is to turn every strategic investment into a reusable public good. Imagine an open library for scheduling between orbital nodes, a public dataset of radiation events on commercial chips, or shared security protocols for remote access to orbital clusters. These are assets the private sector can leverage, but they remain anchored to a collective mandate. Likewise, Earth sciences must return to the forefront. An orbital computing network capable of processing locally enormous volumes of hyperspectral and radar constellation-wide data could unlock hydrological forecasts, wildfire monitoring, and agricultural yield estimates in near real time, cutting the latency between observation and public decision. Here, the rhetoric of innovation becomes truly political. Who decides which datasets take priority? Who ensures that access doesn't become a barrier? And as governance is redesigned, the launch calendar continues to set the industry's pulse. Weekly commercial missions no longer surprise anyone, but behind every routine There are micro-revolutions. Boosters reused for the 15th time. Upper stages rethought to minimize leftover propellant at mission end. Multi-client deployers orchestrating dozens of satellites in precisely timed separation windows. Europe, after years of difficulty, is beginning to rebuild a production chain with new configurations, while across Asia national alternatives are emerging, delivering scientific and commercial payloads ever more competitively. It's not a zero-sum championship. More players means more redundancy, and, if well regulated, greater resilience in our orbital economy. Among the launchers drawing the most attention are the giants designed for voluminous payloads and next-generation constellations. Heavy rockets promising not only larger satellites but entire integrated modules, orbital tugs, transferable propellant, foldable radiators to be inflated like sails, broadband phased array antennas. Their maturation isn't just about spectacle missions. If marginal costs truly fall, they open the door to new logistics, transporter, missions that become regular buses for startups and universities, or propellant depots enabling trajectories previously impossible economically. For those dreaming of data centers in orbit, it's the difference between a demonstrator curiosity and an infrastructure that can grow by modules. The picture wouldn't be complete without looking at the human dimension. An administration that bets on speed must demand transparency when speed meets safety. This means strengthening certification channels for crewed missions, but also introducing technical audits for dense constellations, with shared simulators for orbital traffic and codified right-of-way rules. It means protecting scientific missions from light and radio pollution, setting practical and technical limits. It means funding debris removal not as a symbolic gesture but as the purchase of a real service, with mandatory targets for those exceeding certain launched mass thresholds. And above all, it means making the public understand why every choice matters. Explaining why a nighttime launch window reduces air traffic impact, or why a near-polar orbit offers a compromise between global coverage and cross-collision risk. If human exploration is to remain the beacon, the agency must also resist the temptation to merely shift budgets while leaving flaws intact. A sustainable lunar program isn't a sequence of flags and photographs. It's logistics, refueling, communications infrastructure, habitat life cycles, and mechanical interface standards allowing modules from different suppliers to coexist like pieces of a Lego set. It's also an aesthetic and cultural choice. To build something worth maintaining for decades, justifying regular cargo missions, long-term biological experiments, robotic construction sites paving the way for crews. In this sense, the convergence between new orbital computing architectures and human presence isn't far-fetched. A lunar outpost with onboard pre-processing capabilities reduces dependence on Earth links, filters, raw datasets, and optimizes downlink windows, freeing bandwidth for emergencies and telemedicine. The second half of this story, the one where decisions become reality, unfolds in details that at first seem irrelevant but actually decide everything. Take latency. For certain AI workloads, such as distributed training with frequent synchronizations, all reduce gradient exchange. The logical distance between nodes determines scalability. In low Earth orbit, a point-to-point link between satellites separated by a few hundred meters can reach physical latency of mere tens of microseconds. But once you move to a wider topology with multiple hops, the avalanche effect is immediate. That's why the most credible projects choose hybrid architectures. Local training on tight node clusters, inference on sparser nodes, and a pipeline that moves compressed models more often than raw data. It's a lesson already seen in terrestrial supercomputers, only here, every cable becomes a laser beam, and every rack a satellite with attitude thrusters. Another crucial detail is managing energy peaks. Deep learning algorithms aren't stationary. They have phases of intense computation alternating with I/O and synchronization. In orbit, this pulsation must synchronize with the power profile of the panels and the dissipation capacity of the radiators. One solution is to orchestrate workloads into solar and shadowed phases, shifting the hottest computation into orbit segments with favorable energy flux and reserving communication phases for the cooler parts to help radiators. Another is to use solid-state batteries optimized for many microcycles, accepting programmed degradation offset by modular ease of replacement. Here the theme of maintenance returns. Service robots capable of capturing a module, detaching a power unit or accelerator board, inserting a new one, and releasing the satellite with a soft push to restore formation. The issue of digital security deserves a chapter of its own. An orbital data center is critical infrastructure. Command and telemetry channels can't be protected by basic encryption alone. They require verifiable hardware roots of trust, secure boot with remote attestation, rotating keys independent of single vulnerable HSMs, and above all physical segmentation between control and payload domains. In a terrestrial cluster, a breach might mean downtime and lost reputation. In orbit, it can mean a lost asset, created debris, cascading collisions. That's why public requirements should include mandatory red team tests by third parties, simulating replay attacks, selective jamming, attempts to desynchronize attitude thrusters, and the system's ability to enter a computational, safe mode, not just a mechanical one. On the orbital front, sun-synchronous attitude is often cited as ideal for predictable solar illumination, but it's not the only option. Quasi-periodic or resonant orbits can offer more balanced energy profiles for certain latitudes, while multi-shell configurations with different inclinations reduce local density and collision risk. Debris dynamics force us to imagine orbital roads with right-of-way rules and buffer altitudes. A forward-thinking agency can introduce incentives for satellites with reduced cross-sections and radar soft surfaces, and penalties for those lacking reliable deorbit designs within defined timescales. Technology for active debris removal, soft harpoons, electrodynamic nets, magnetic tug capture, is mature for operational demonstrators. Funding it as a recurring service, purchasing kilograms removed per year, would send a powerful signal. And what about human exploration? The most strategic choice is to treat the return to the moon as an infrastructural project, not a string of event missions. A credible cadence, a supply chain that includes autonomous cargo landings, redundant energy plants, fixed and mobile, optical and radio communications with lunar orbital relays, and expandable modular habitats. The elements now being developed for low Earth orbit computation, large area radiators, maintenance robotics, radiation-resilient software, find direct application on the lunar surface, where abrasive dust and thermal cycles demand robustness. A local computing cluster near an outpost could process geological and environmental data on site, support rover autonomy, and run real-time risk models for EVA and logistics. Meanwhile, the commercial ecosystem will continue to expand. Rideshare missions have democratized access to orbit for universities, startups, and emerging countries, but the real frontier is moving from throwing the cube to operating it well for years. This requires reliable buses, standardized control platforms, on-demand propulsion services to maintain orbit, and secondary markets for payloads that change ownership during their useful life. In this context, a major industrial acquisition is not just financial news. It signals a supply chain becoming more vertical, combining those who build platforms with those who sell their data and capacity. Further downstream, clients want products, soil moisture maps, early storm alerts, guaranteed throughput between two fiberless cities. Each link in the chain must communicate seamlessly with the next. Launch schedules, controller availability, and air traffic coordination have become a three-dimensional logistical puzzle. Reducing conflict windows with civil aviation, coordinating NOTAMs, and introducing automation in clearance processes may sound administrative, but they're actually technological accelerators. The more predictable the windows, the cheaper industrial planning becomes, and the easier it is to distribute workloads across shifts without burning human capital. And when political events temporarily stall the engine, resilience makes the difference. interagency protocols, mirror control centers, and cold start capacity for programs that cannot afford continuity breaks, like climate observations or mission support. Looking ahead, the best trajectory isn't one of sudden revolution, but of deliberate acceleration, setting intelligent, measurable public goals, cutting average optical link latency between nodes in a demonstrator by X%, performing robotic maintenance within orbit replacement of a power module, certifying a radiation-resilient AI stack with open benchmarks, and letting the market compete on the how. For the agency, success will be invisible yet profound. Standards adopted globally, reusable infrastructures, young researchers finding at home a place to dream big without compromising scientific integrity. For the private sector, the reward is an expanded horizon, where the line between data center and satellite blurs, and low Earth orbit transforms, piece by piece, into a true industrial zone. In the meantime, we, attentive spectators, learn to read the subtle signals. An evening launch window hinting at a new deconfliction policy. A deployer with tighter timing revealing confidence in separation models. A seemingly minor announcement about a next-generation radiator that, in truth, unlocks an extra half megawatt of net power for a cluster. It's this quiet attention, more than slogans, that tells us where we're heading. And perhaps it's right here that strong leadership will make the difference, not by announcing the next, biggest ever, but by patiently and rigorously building the scaffolding that allows the system to stand on its own, even when the corridor clocks fall silent. If you've made it this far, it means you love curiosity as much as we do. If this journey has inspired you, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.